The third of our introductory slices, we're going to have a look at some curious language features within C++. And most of these features are aspects that a lot of Java and C# programmers, if they encounter in C++, might scratch their head and go, well, why would you do it this way? That's maybe isn't such a great way to do things. And most often that is exactly the right reaction to have. So we're going to look at some of the characteristics that C++ have, a few of the language features. We'll generally pick ones that are from the early days, but because C++ maintains its backwards compatibility, they have fed forward into current modern C++ as well. So we'll start off first of all with the notions of declaration and definition. Maybe you haven't made a strong differentiation between the two, but it is important in C++ to understand whereabouts we are defining something and the instances within which we need to provide a forward declaration of something. So we're thinking here about the compiler. So it was phase 3 based on the previous slice. And I've got a little fragment of C++ here over on the left-hand side. We're declaring a method called foo, and it does some stuff on line 2. Line 4, we have our main method, so this is where we kick off our execution. And down in line 6, we're invoking foo. So we've defined it in lines 1 and 2, or wherever it is, but it's been defined above. When we get down to line 6, we see that, okay, here we have a signature method called foo, doesn't return anything, there's nothing be passed into it. And the compiler at that point, because it knows about foo, foo's been defined earlier on, can check to see, am I invoking this correctly? Have I made any assumptions about the return type? Am I passing in the right type of parameters? So on and so forth. That's unproblematic, it'll compile. The example in the middle will not compile in C++, even though it would compile in Java and C#. In this example here, all we've done is we've taken the definition of foo from the top down to the bottom. So now it occurs after our main method. When we're compiling, we come in at the start of the file. We start on line 1, we go on to line 2, to line 3, until we reach the end of it. So that's what the compiler will do. It'll start off on line 1, our main method. It'll encounter line 3, the foo method. And it'll say, okay, here we're trying to call a method called foo, but I don't know anything about foo. I've never encountered anything about foo before. So the compiler at this point will actually stop. And it will say, you're trying to invoke foo, but I don't have a clue what foo is or if you're doing it correctly. So it doesn't know anything about it, so it can't check to see if it's been correctly called. If we wanted to get around that, we could provide a declaration of foo before we actually use it. And that's what we do in the example over on the right. So in line 1, what we have done here is we have the full method signature. So it's a method called foo, doesn't return anything, doesn't make any parameters. But if it did return something or had parameters, we specify them there. We're providing a semicolon immediately at the end. So we are declaring it. We're saying that there is a method called foo. I'm not saying yet how it actually works. I'm not defining it. I'm just declaring, saying that it does exist. So it means that the compiler, whenever it reaches line 5, it knows about foo. It doesn't know how foo works. We'll get onto that later, but it knows there's a method and it takes in these parameters and returns this type. So it's able to check to see, have I correctly invoked it? And let's assume I have. Down at line 9 then, it actually encounters the definition where we actually define what it is foo does. So it's important to understand here that in C++, if we want to use something, either we need to have to define it before we use it, or we have to provide a declaration that it exists before we try to use it. You might think, why? Why on earth would you do this? It seems to be an unnecessary step. It seems to be rather a dumb thing to do. Why would you not just have a 2-pass process? In the first pass, you would scan on down through the program looking for anything that defines a function. You would then have a nice table where you have all of your defined functions. And then the second pass, you can go through having a look at how things have been used. And indeed, basically all modern compilers and good languages then will be multi-pass. But in terms of understanding why C++ is structured to enforce these rules, you have to remember that we're talking about a language that's, go back to the days of C, more than 40 years old. So back then, it was a rather different world where if you had your source code and it was on a magnetic tape where memory wasn't particularly bountiful, it actually would have been a big ask to load the thing once, to have your table, and then to rewind the tape back and to load the tape in a second time. So all of these things could have actually increased the compilation process in terms of its duration by quite an amount. So it was easier back then, in more simple days, to require the program to be written in a way where things were either defined or forward declared before they were used. Does not apply at all today, but this is a consequence of C++ in terms of maintaining its backwards compatibility, that this is still something we have to deal with, even though it's not an issue and hasn't been an issue for some decades. It's such a common need to do that header files actually emerge from it. So again, this goes all the way back to C before C++, where programmers found that they were declaring an awful lot of stuff up front. By way of convenience, you could actually just have a header file. So you would include a single header file, and in that header file you would put in all of your declarations. It was a way of grouping them all together. So that came in with C. So C has .c files and .h files. In C++, you can still use that for declaring aspects, but remember C++ added on object-oriented aspects onto C. So it's very common in C++ if you are declaring and defining a class. So you have methods and functions in an interface. In the header file, you include the interface to that class. So the header file contains all of the declarations and any sort of public data. In the CPP file, you then provide the actual implementation of the different methods. And that's a nice aspect. It gives us a way of to one degree, separating out implementation from the interface of that particular class. And that's generally a good principle in terms of object-orientism. Now, it says at the bottom, they're not without their problems or complexity. So we'll have a look at some of these aspects. We've got a few examples here. So this ties into the notion that in C++ that each file is independently and separately compiled. So I've got my project. In my project, I've got two CPP files which are part of that project. Over on the left, I've got my helper CPP file. And within this, I'm declaring a class. Within that class, I've got a couple of public methods, one method, help, and I'm declaring an integer called help code. And down at the bottom, I'm saying how the help method is actually defined, what it does. So fair enough, that's my helper class. Over in main.cpp then, I'm creating an instance of my helper class in line 3, and I'm calling the help method in line 4. The problem is, because each of these files are compiled individually, in the current main, it doesn't make any mention or reference to helper, other than saying I want to create an instance of it and then want to call it. So when the compiler gets down to line 3, it's going to say, okay, I've got to create an instance of a class called helper, but I don't know anything about helper. I don't know how it's defined. I don't know what it is. So at this point, the compiler is going to stop and say, you asked me to create something, but I don't know what the thing is. So it's not visible by default within it. And that means that in any of our CPP files, we have to be put in the effort to make sure that the things that we need to compile it are visible, are included within it. So fairly straightforwardly done. This example here, over in the left-hand side, you can see we've taken what had been our helper.cpp and separated it out into a header file and then the implementation file. So in the helper.h, we are declaring a class called helper. We're saying it has a help code int and it has a method called help itself. And in the helper.cpp, we're actually given the method, but we're defining them. We're saying how they work. You notice on line 1 of helper.cpp that we include a hash include. So this is a preprocessor directive. It basically says go to whatever's after it, in this case helper.h, and paste in the contents of that source file into this one. So whenever the preprocessor finishes executing line 1 in helper.cpp, it will have taken the entire contents of helper.h and pasted those into helper.cpp. That's what that preprocessor directive does. Over in main.cpp, we're doing something exactly the same. We've got a hash include helper.h. So whenever it encounters that, the preprocessor will go off to helper.h, copy and paste in the contents. And that gives a changed CPP file, and that's what gets to be passed off to be compiled. In this case, we've included in our declaration. So down in line 5, we can actually see, yes, we're constructing the class. We now have access to the constructor. We can do that. In line 6, we're calling a method called help. We can check to see if it's there, if it's been correctly invocated, and so on. So all of that sort of works and hangs together. But here's an example of something that doesn't work. Preprocessor, the compiler, not particularly friendly. What I mean by that is that they will do exactly what you ask them to do. So here's an example, main.cpp. In line 1, we hash include helper.h. In line 2 and 3, we're including other things, and we'll get onto the different syntax in a second. But here we're including a string library, standard library, and an IO stream, standard library. In line 4, I re-include helper.h. Now, in line 1, preprocessor directive. Preprocessor will say hash include helper.h. Fair enough. I'm going to go off to helper.h, take the contents, paste it in. I'll paste in the contents of string, IO stream, and in line 4, it'll do exactly the same thing. I'll go off to helper.h, copy and paste it in. And I'll then say to the compiler, there you go, there's the code I would like you to compile. The compiler will go through the extended file. In helper.h, it'll see, oh look, we're declaring here a class called helper. Brilliant. When it eventually gets down to the extended or expanded line 4, it's going to find another declaration for a class called helper. And at that point, the compiler will give up and it'll say, hold on, I've got one declaration of a class called helper. Now you're telling me there's a second declaration. I don't know what to do with this. So compilation will stop at that particular point. And it's really our fault. Our fault as programmers for tricking the poor compiler, for sticking in something that's going to result in multiple declarations, which the compiler will not be able to handle. Now, it's quite probable, I would hope, that you'd be saying, hold on, I'm not going to do something as silly as putting in that silly error. And if I did put in something as silly as that, well, I deserve everything I get. But actually, sometimes well, other than a language feature we'll get on to secondly, if we didn't have this language feature, it actually could be hard to avoid doing that. Here we have an example here. So look in the middle, first of all, we've got mylib1 and mylib2, because I'm not very good with naming things, and they're both my libraries, and I've created these two libraries. And inside both library, I'm making use of helper.h. So helper is the class I've created that's incredibly useful, that I use in all of my libraries. So mylib1 includes it, mylib2 includes it. Fair enough. Inside main, so somebody likes the libraries that I've created and wants to use my libraries. So in line 1, they say, I want to include mylib1. So anything I have declared within that, I'll make it available within main.cpp. And everything available within mylib2, I'll make that available as well. But here's where it gets interesting. So inside mylib1, we include that. So the preprocessor will go off to mylib1 and we'll say, okay, I've got to paste everything in there. But mylib1 contains another preprocessor directive. So before it pastes it in, it'll execute those preprocessor directives. So I'll go to helper.h, it'll paste the contents of that into mylib1.h, and then paste the complete contents of that into main.cpp. And it's going to do exactly the same thing with mylib2, which will trigger the other preprocessor directive and result in helper.h being copied into that. So long story short, again in main.cpp we will end up with two helpers that the compiler will not be able to process or to handle. Even though that may not be my fault as the person creating main.cpp, it's the fault of the person who put together the libraries. So there's a few pieces of guidance there. Generally, in terms of header files, only include things that you need to include, and guard against accidentally or unavoidably including multiple files by putting in guards. Now, if it's unavoidable, it means you can't avoid it through design. How do you deal with it? There's actually two common ways that you do deal with it in C++, and they're both shown here. The first one, we're using preprocessor directives to get us out of this. So you have a look at line 1, we have preprocessor directive if not defined, and then you have some string of text after it. So if not defined, in this case it's a label foo included, then we will execute the following. Down in line 6 you see end if. So lines 2, 3, 4 and 5 are conditional on that if statement. If the if statement is true, we'll do it. If the if statement is false, we won't do it. In line 2, we actually define foo.h, or foo.h included. And in line 4, we have our full declaration of the class. So the first time we go into this, we will not have that label defined. So we will duly define it and then include it. The second and the third and the fourth time we try to include, we do include, line 1 will be true, so we will automatically skip over that. So it gives us a way of only doing it once. And that's the standard correct way of doing it. You might sort of go, it's a little bit hassly, you've got to sort of put this standard stuff in. It occurs so frequently that in a lot of languages, the second example at the bottom, you have another preprocessor directive, pragma once. And if you get that, it basically means only include this header file once. Now, C++ does it because this is just the way the language was set up. If you're sitting thinking about current modern languages, they don't do this. And indeed, when people were sitting down designing Java and C#, they thought, well, what things don't we like about other languages and how do we avoid them through the language design? Because ideally we shouldn't be going to the programmer and getting the programmer to do the sort of housekeeping. It's wasteful. Right, let's make things a little bit more potentially complex or certainly confusing. And you see this is entitled the somewhat confusing multiplicity of header types. There's different types of headers. They've changed over time from C to C++ and so on. But because C++ has evolved in a way where you have maintained backwards compatibility, it hasn't thrown anything out. And that means that nowadays you get a lot of other baggage that comes along. Now, if you're a modern C++ compiler or programmer, you avoid most of this baggage. You stick to the current stuff. But if you're looking at examples of C++ online, you're likely to see bits of this, bits of this, bits of that, which actually do add to the complexity of it. But we'll go through a few of them here. Now, we've seen this in the earlier example, that there's two common ways where you can actually include something. One is using our angled brackets, and the other is using quotes. What's the difference between them? If we use our angled brackets, it is a way of signifying to the language that the header file that we have after it is a standard part of the language. It's one of the built-in libraries. And that's all that denotes. It denotes you should go off to a built-in directory to try to get this out. If we put quotes, we're saying that it's a header file that belongs to the project. And then we should go to a different directory to try to find those header files. So effectively, it's just simply a way of letting the compiler know where it looks to find that header file. Unnecessary, and indeed it has been replaced in C++ through namespaces, and in most Java, C#, when you're talking about packages and things like that, there's a better way of being able to specify where a header file or something you're trying to include actually exists. But we have both. Also gets a little bit more confusing. Remember, C++ built upon C. C defines a number of header files, as does C++. The convention in C was that if you had a header file, for example, let's say math. So math contains a number of mathematical functions for sine and cosine and floor and ceiling and things like that. So in C, the standard header file for math is math.h. And you can see the example down here in line 1. If we wanted to include the C header file, we would say math.h. And because C++ is backwards compatible with C, we can do that in C++. But when they created C++, they also created C++ versions of the C header files, which in most cases are more or less the same, though there can be small differences. So if we wanted to include the C++ version of the C header, we would use the syntax or the particular statement shown in line 2. So there's no .h, but we're including CMath. So anything that starts off C something, this is the C++ version of the C library. Fair enough, only slightly confusing. This is what makes it a little bit more confusing. So sometimes the C and C++ headers are virtually identical. Other times they actually can be very different. And there's no easy way of doing this other than knowing what is within it. And I'll give you an example now. In Java, or indeed in C#, integers are defined. They are 32 bits in size, unsigned integers, or signed integers. So basically, they are declared or defined. In C++, they're not. Integers can be in different sizes on different platforms, potentially. So in C and indeed C++, there's a limits file. And the limits file tells you just how big the things are in the platform that you're going to be compiling for. So you'll know if an int is 32 or 64 bits or whatnot. So you have 3 examples here of limits. The one in line 1, limits.h, is the C version of the limit. So it's how big an integer and a float is in the C language for whatever platform. The C limits file, line 2, is the C++ equivalent of the limits.h file. And if you open both up, they'll basically be the same. But we also have in line 4 limits. And this is the C++ limits file. It's not the C++ equivalent of the C limits file, it's just the C++ limits file, because this is not at all confusing. And inside that actually will be quite a lot different, because it'll contain some stuff about namespaces or other related ones. So it is confusing. It's part of the cost of being able to explicitly maintain clear backwards compatibility, as opposed to saying we're going to burn bridges and deprecate and remove certain elements as time progresses. There's a large, well, actually I said large, it's not that large. In comparison to a lot of the current languages, it's a modest collection. So C++ provides you with a useful, modest collection of built-in libraries, so MAS and IO streams and other stuff, known as the standard library. There's quite a few other good third-party libraries, so Boost is one of the more popular ones that you will find people quite often plug into C++ to provide enriched functionality. But as with all programming languages, it's good to get to know the libraries, because you don't want to be reinventing the wheel. You want to make use of what is available out there. And a bit at the bottom, C++ libraries, standard and other, place their definitions in namespaces. So we're going to look at namespaces very briefly here. And it was sort of a later, it's an addition or an aspect that we take for granted in Java, for example. In C++, it is good to use them because there are clear benefits or advantages to doing it. But we'll show you an example of why we actually would need one first of all. So namespaces let vendors package classes and functions within named spaces. Fair enough. They help to better structure large projects and avoid naming conflicts. So let's show you an example of what we mean here. So we've got lib.a and lib.b, and let's assume they've been created by different people, different companies. Lib.a and lib.b both define a proc method. No parameters, returns an int. So I want to use the functionality of both these libraries. In my class, I include the header files for both of the libraries, and that makes available all of the things that they declare within them. But I've got a problem, because in line 6, when we're trying to call proc, well, I've got a proc that came from lib.a, and I've got a proc that came from lib.b. the compiler won't know which one it is, so it won't be able to compile this. It'll complain about a naming conflict. So here we have an issue. What do we do in that case? Do we say that names must be unique? That means that the library A, whoever gets in first gets to declare it. And that wouldn't really work because quite a lot of methods, for example, toString, something like that, these are things that maybe a lot of objects we would want to be able to define, not only one. So the notion of saying that each method must be unique, you only have one named version of it, that doesn't really hold. So we have to have a different way of being able to say that I want to call the proc method that belongs to something, and whatever that something is. So we'll use a namespace then to say that we can call the proc from a certain namespace as opposed to the proc from a different namespace. And how we differentiate, you can see at the bottom. So a colon colon, so colon colon is the particular syntax to say that we are accessing or going into namespace. So a colon colon foo is different than b colon colon foo. So in one case we're talking about the foo method that belongs to namespace A, and the second case the foo method that belongs to namespace B. So doing that then, it gives us a way of being able to differentiate between them. And I'll show you a few examples of how we use them here. So the C++ standard library, they're in a namespace known as std. Slightly unfortunate naming, but that's what they call it, so it's a standard namespace. So in line 1, the example at the top, we're including preprocessor directive IOStream. So IOStream is input-output stream, and it'll contain a bunch of methods for writing characters out, reading characters in, doing stuff like that. In line 3, we're making use of the cout, character out method, which is declared within IOStream. So we're saying line 3, std colon colon. So we want to access a method, a function called cout, that is part of the standard namespace, and that namespace will be defined within IOStream. And that's good. Then we're passing into that a character string called info, and we're passing into that. Now endl is the end of line character, which can differ between platforms. Again, it's something that is defined within the standard namespace, so we do standard namespace colon colon endl. So in this case, cout and endl, we are explicitly saying that they are defined. It's the ones we have within the standard template library that we want to use. It means that I could come along, I could write my own library with my own cout function, and it wouldn't conflict. I could say that I want to go to my namespace and use my cout function. Perfectly fine. You might think the example line 3 is a bit sort of verbose. The middle example then shows you how you can make this a little bit more concise. So in line 2 of the middle example, we're using namespace std. So this is basically saying that I'm going to assume that my default namespace is the standard one, and if I don't make something explicit, assume that it is actually from the standard namespace. So line 4 then, I can use cout and use endl, and it's taken for granted because of line 2 that it's the standard one. Using namespace standard will include everything from the standard namespace, so you get kitchen sink, everything thrown in. If I wanted to be a little bit more precise about it, you see the example at the very bottom. So here we got lines 2 and 3 at the bottom of the example, where we're saying that we're using cout from standard and endl from standard. So it's not including the whole thing, it's just saying that anytime you encountered a cout, it's the standard version of it. Anytime you encountered NL, it's the standard version. And again, you've got your line 4 down there. So this is what we want to do. This is the way we'll be structuring our programs to make sure that we can write stuff that will be differentiated or remain aside from others. So key takeaways from this. I mean, we covered a few points here. I specifically wanted to cover things that a Java or a C# program would sort of look at, a programmer would look at and go, that's curious, why would you do that? And they are features within C++, and it's because that it has quite carefully maintained backwards compatibility all the way back to the C programming language. And there's a benefit to that, remember. It means I can take a program that's been written 40 years ago, and there's a very high probability it'll be able to compile and run in today's compilers. So you get that. It's good for legacy systems. But it does make our life as programmers more complicated, because as the language has evolved and changed, you get baggage, that comes along, and it makes it certainly more difficult to learn it, because if you're looking at examples, you might see some examples written one way, some examples written another way. So these are challenges that we will have to live with. Important thing, I suppose, to understand here is that languages do change, they do evolve over time. So languages are not a static thing. Programming languages, their capabilities, the syntax, the structures we use, they all do evolve slowly, but nonetheless they do evolve over time.